All right, so let's start out with any questions.
Okay.
Emily or Noelia, one of you.
For test 3, I just wanted to make sure I know which chapter it's all on. The last test. Yeah, the last test.
All right, so it will be on the stuff that potentially will start today.
Okay. So the master test that we did, 8 through 10, is there a test on that stuff?
Yeah.
Okay.
No, I started really early on not doing a test on that material because I felt that I knew what the test results were gonna be, so why waste the day?
Okay. I just wanted to make sure.
And Noelia?
I was gonna bring up my master set question.
Okay.
I'm just a little unsure about 8. If a launcher shoots a ball horizontally from a height of 1.5 meters, the ball lands 8.2 meters away from the base of the launcher, and it asks how fast is the ball launched from the launcher, and then if the ball is then fired straight up with the same speed, how high will it go?
All right, this relates directly to the lab that I'm planning for us to do today. So it's being shot horizontally. I'm gonna use different numbers.
Okay.
So it's shot from a height of 1.5 meters, and it's gonna land, we'll just say 7.3 meters away. Let's pull out this. Is this level? Okay. And yes. So we'll go with that. These two are about the same size. All right, so what's gonna happen? Get a copy. There we go. So when I pull this, basically there's a spring inside that's gonna suddenly push this rod that's right here, so everyone can see it, this rod right here, that way. When it does, this one, the rod's basically gonna slip out from the hole here, so this should be dropping close to straight down, and this one gets shot out. And to try to avoid it breaking anything, I'm gonna push the glassware out of the way. I think it's gonna miss that, and this one's gonna get shot over here. Now, if it's shooting too far, I'm gonna miss the table and we'll just redo it. So the question is, now some of you probably already know because you have known this stuff already. Some of you have read the chapter or seen the video, but who says that the one that falls straight down is gonna hit first? You can go for that one?
Yeah.
All right. Who says the one that's projected out is gonna hit the ground first? And who says they'll hit at the same time? I don't know where people haven't voted yet, but the majority seems to feel it's gonna be at the same time. You should have heard the same sound at the same, they should have hit the table at the same time, so it should have sounded like one sound when they hit, which I believe it did. So the essence of that problem and of the lab and of, well, the nature of projectile motion, the time it takes for something being shot horizontally, the time it takes for it to fall this way is the same amount of time it takes for it to go this way. Now this one is moving faster, but it also is traveling farther and it all balances out. It comes down to the fact that the force acting on both of them is the force due to gravity. The only acceleration that's involved in this is downwards, and that acceleration rate's the same. So, if I know from the height from which it's shot, I can figure out what the time is it takes to fall. And so, I know that displacement for something starting at rest ½ AT squared. So 1.5 meters. .5 meters equals 1/2 times 9.8 t squared. This is the formula, the Hewitt version of it. It's the distance is equal to 1/2 times gt squared. It's a little bit more generalized than what I've written. Is a little bit more generalized than what Hewitt did, but it still works. And so 1.5 is equal to 4.9 t squared. That's just 1/2 times 9.8. We're trying to get to time, so we're going to start peeling this stuff away. So first we get rid of the 4.9. And so t squared is equal to whatever magical thing that is.
0.306.
0.306. And now we get t by itself by taking the square root of both sides, which is
0.553
units.
seconds.
All right. So we now know how long it is in the air. Now horizontally, there's no acceleration because once it is launched, I should specify, once it is launched, there's no acceleration horizontally acting on it. So if I know the distance it goes this way, and there's no acceleration that way, then I have my zero acceleration formula. That distance is just equal how fast you're going times time. If the acceleration is zero. And so it's 7.3 is equal to how fast you're going times 0.553.
How did you know acceleration was 0 again?
Once it is launched, what are all the forces acting on it?
Just gravity.
And which way does that act?
Downward.
Therefore, the only acceleration is vertically.
So it's not changing, I guess.
Horizontally, it's not changing at all.
Okay.
And so this is the vertical equation here. And this is the horizontal equation here. And so the speed ends up being somewhere around 14 meters a second.
13.2.
13.2, right? Which is about 30 miles an hour.
So what about when if the ball is in fire straight up at the same speed, how high is it
Ah.
going?
All right, so now you know how fast it's going. And so now it's going to be launched. I know it's initially going at 13.2 meters per second. Now, in reality, this force right here is caused by acceleration from the rod and the spring. There's going to be a little bit less than that if it's launched straight up because it's also fighting against the force of gravity, but not significantly, so that's why I ignored it. So 13.2 meters per second being shot up. I know up here it's going 0 meters per second because you want to know how high it's going to go. And so now it's a question of how high will it go? I know the acceleration is down at 9.8 meters per second squared. And it really comes down to how you want to solve it. We could solve for time.
Can you divide by the acceleration? I mean, can you divide by like 9.8?
If you do that, yeah. So that would be from the acceleration is the change in velocity over the change in time. If I just, let's just make up positive. So my acceleration would be negative 9.8, and that's equal to my change in velocity, which is 0 minus 13.2 over time.
Negative because it's going down.
Yes, because that's going down. And this will be negative because you're losing speed. Or you're losing, you go from 13.2 to 0. So the math problem you're dealing with is negative, well, negatives will go away. 9.8 is equal to 13.2 over t. That's the math problem. And you can turn anything into a fraction by putting it over 1. Now we have two fractions equal to each other. You multiply the diagonal, you know, divide by what's left over. So 13.2 over 9.8 is the time.
1.34
seconds. And now we need to know how far up it goes. Now this equation over here, you can use, this is starting at rest. But it also works if you're ending at rest as well. And so using that equation, 1/2 times 9.8 times 1.34 squared. So 8 meters. What'd you get?
That's 8.93.
8.93. Alternatively, I know I'm starting at 13.2 meters per second and I end at 0. So my average velocity is, well, the average of those two numbers, which is 6.6 meters per second. And so I could multiply 6.6 times 1.34. And presumably get the exact same number. And sorry, Noelle, you started with a question and I keep getting farther from you.
No, it's fine.
I assume glare is an issue.
Yeah, I can see it now.
Okay, sorry about that.
Where'd you get 6.6 from?
The average of these two numbers.
So where would you say that it started from?
Where would it say what?
Okay, so you found the distances with, but where did you start from?
Define, I interpret that two different ways. You're talking in solving it, where did I start, or physically, where would I? Ultimately, this is how far up it goes from whatever point it was shot.
So you're starting at 0?
Yes, starting at 0, yes. In the problem, did I specify you started? I asked specifically the how far from point of release, right?
No, just in B, it says that the ball is then fired straight up at the same speed, how high will it go? But it also says, give me the height from the point at which the ball leaves the launcher.
Yeah, so as opposed to, from the ground or some other reference point. The reference point was, it's shot from 0.
For number 5,
Okay,
can we
okay.
switch?
Other questions on this?
Can, you scoot just a little bit so I can, sorry, thank you.
Whatever you want to.
Thanks.
Sure. All right. If she's writing this down, any other questions on this? Brianna.
Okay. For number 5, with the ring turned into a disc,
Yes,
what difference does that make?
you're changing the moment of inertia.
Okay.
And when the moment of inertia changes, because you're now taking some of that mass that was out here and bringing it closer in, you are reducing the moment of inertia, which increases the angular velocity.
Okay.
You'll spin faster, it'll spin faster.
But how do we figure out what that is?
What that formula is for moment of inertia? Or,
Well, with the information that we're given, it just says 10 kilograms of mass is formed into a ring with a radius of 5 meters.
okay, so the formula for moment of inertia for a ring is mass times the radius squared. The formula for moment of inertia of a disk is 1/2 mass times the radius squared. So I gave you mass and radius. So it comes, once you recognize the formula,
Yes.
plug your tongue to get I.
Where would I see that?
In the textbook, page 128,
Really?
134, somewhere
Because
there.
I looked for so long, but okay.
So on number
call the
5,
disc
you wouldn't
on
use
the
the
cylinder.
angular momentum equation?
Okay,
The
so,
disc is a cylinder. That's
Yeah.
wrong.
oh yeah, disk is a cylinder, the same thing.
I don't know why, but in my head I was thinking like a CD disc.
That's what I.
Oh,
Yeah, thinking like a DVD or something.
well,
Yeah.
that works too, I mean,
So is it more like a frisbee disc? A cylinder?
it's just, it's a, I think from a general point of view, you'd consider it a disk if the height of it is less than the diameter. But the only difference, but in everyday life, a cylinder, you know, if I had something round like this, that would be a cylinder, and if we're flat like this, we'd call it a disk. But
I was
there's no
so
difference mathematically.
confused.
But that makes sense, cause I was like, well, a CD is a ring too, it's got a hole in the middle. I was very confused, but that's my bad.
All right,
And R is for radius?
R for radius.
Okay, what about the?
Like, there's another question about angular momentum in this problem.
No, I got 1,000 for that.
What about the 20 rad over second, what about the,
That 20 radians?
yeah, radius,
So you can't use the angular
right.
momentum equation.
Well, you will. So, in this problem, it's a conservation of angular momentum problem. You're going from a distribution of mass, spinning at some speed to a new one. Again, similar to the skater pulling his or her arms in. So, my initial angular momentum is equal to the final angular momentum. And that is equal to I times omega.
Yeah.
That angular momentum, there's two formulas. One of them is you're multiplying I times omega. The moment of inertia times the angular velocity. I gave you this, and I gave you enough information to find that. I gave you enough information to find that, so you just solve for that.
So 20 is not the velocity?
That was the 20 radians per second?
Yes,
Yeah, that's the angular velocity.
okay.
So you couldn't just do it, cause I'm
So you would do the I disc 0.5 times 10. Squared.
No, because I have it in MDR, so you times them all together, so.
All right,
After you get the information from that one, right?
NVR works if it's, in essence, what's called a point mass. If I shot putty, if I had ruler dangling like this and I shot putty at the ruler, so it hits the ruler and makes the ruler move, that's when I would use NVR. NVR does not work as well if you have a distribution of mass and not everything is traveling at the exact same speed. So, now, in the case of the ring, if I've got all the masses here and it's spinning about its center, everything's moving the same speed, you could use MVR for the left-hand side of the equation, it would actually work. But it won't work for the right-hand side of the equation. Because M is the same, the overall radius is the same. V, well, omega is the same, V is not quite the same for both. That you're given the look of, I just spent 2 hours working on that one problem and it turned out it was for nothing.
I mean, no, I didn't spend 2 hours on it, but, so the WI is the initial velocity, you said?
Angular velocity, initial angular velocity, final angular velocity.
So it is gonna change, or no?
So when I changes, omega will change.
I'm still confused on how to solve it.
Say it again?
So I'm still confused on what to do.
Let me run through a similar, but not the exact same problem. The problem is simpler than you think. Conceptually, maybe not, but in terms of mechanics of what you act, how to solve it, it's a lot simpler than I think some of you are feeling right now. All right, so let's start out with, it starts as a disk and changes, so disk, solid, and it changes to a stick that's rotating about that point right there. I know the formula for the disk spinning about its center is 1/2 mr squared. So let's come up with a mass of 2 kilograms and R is 3 meters. So the moment of inertia of the disk here, 1/2 times 2 times 3 squared, or 9 kilogram meters squared. I know that the moment of inertia of a stick rotating about its endpoint is m